Now, let's start with the examples. As we said before, let's take a simple example, a very simple example. We are given a simply supported beam here, and we are just requested to get the reaction at A and the reaction at B for this beam to be in equilibrium. The distances, let's call this D1, let's call this D2, let's call this D3. We're not going to use numbers, and F1 and F2 are known, and it's only two unknowns that we don't have. How do I proceed in this kind of case? And I'm also told like we need to neglect the weight of the beam. Now we don't have to consider the weight of the beam in this case, or the self weight of the beam, or the self mass of the beam. But how do we get RA and RB, F1 and F2 being known? We're not going to use the values. We're just trying to define the principles of solving this kind of questions. Now, how do we proceed? First of all, we need to redo the free body diagram of our system. And the free body diagram of our system will be something like this. Our roller support as it's at B, our pin support, we have F1, we have F2, and the distances are given, D1, D2, and D3. How do I get the unknowns? Support reactions. Support reactions, which are the unknowns? I'll first of all look at them. This is a pin support, and I know that when I have a pin support, I should expect to have two components. Which one is RAH, and the other one is RAV. And on this side, I only have one. I have a roller support, and by theory, I know that the roller support has one direction of the reaction. Now, how do I get the unknown? RA and RB. For my beam to be in equilibrium. Already, if I'm told that my beam should be in equilibrium, I should think about the three equations of equilibrium, which will be used all the way in this subject. Now, if I have to use the first equation on this first equation to solve for RA or RB, everybody will agree with me that horizontally, do I have forces that are horizontal? I don't see any force horizontal, but I know that at a pin support, I'm supposed to have an horizontal component. But for this horizontal component to exist and to have this beam in equilibrium, the sum of horizontal forces should be equal to 0. How many horizontal forces do I have? According to the theory, this normally should be an horizontal force, but because it's on its own, RAH pointing toward positive values of x will be equal to 0, because that's the only force that I'm supposed to have horizontally. I'm saying the only force that I'm supposed to have horizontally so far, because there's no other horizontal force. And according to the equation of equilibrium, sum of forces projected horizontally should be equal to 0. Therefore, RAH will be also equal to 0. And as a consequence, RAV will be equal to RA, which is the resultant. Now, that's horizontal. Vertical, if I check with the second equation of the first condition, sum of the forces projected on Y, on the vertical direction, should be equal to 0. Let me look at the forces that I have vertically. F1 and F2 are known, and they are going towards negative values of Y. I can give them minus, or I can give them positive. That's not a problem. or let me keep them. Yeah, let's do this. Minus F1 minus F2 plus RA, because it's only one RA, plus RB is equal to 0 according to this. I'll find myself with this situation, RA plus RB equal to F1 plus F2. And this equation has two unknowns. Those are the two unknowns that we are looking for. Therefore, this equation is not going to help us to solve for the unknowns. Let me take the third one. The third one is the one that is focusing on the moment. Everybody can see that I can use, let me use the condition of equilibrium, dealing with the moment, sum of clockwise moment, algebraic sum obviously, clockwise and anti-clockwise moment should be equal to 0. And let me do it for both sides, because the moment, these two forces are creating two opposite moments compared to each support. Let me start with the sum of moment about support A. At support A, what's going to be the moment created by F1? Everybody can see that F1 being here, F1 will create a moment, a clockwise moment. It will be, that moment will be F1 times the perpendicular distance, which is D1. F2 will also create a clockwise moment, call it positive, times the perpendicular distance, which is, what is the perpendicular distance? It will be D1 plus D2. That's the moment arm. And the reaction, which is an opposing force, the reaction will create or will define a moment that is opposed. And that will be RB, creating an anti-clockwise moment, and the moment arm will be, the distance is D1 plus D2 plus D1, or D3 plus D2 plus D1, which can be known as the length. Then RB times the length, knowing that the length is D1 plus D2 plus D3. Now, and this algebraic sum should be equal to 0. With this equation, F1 is known, D1 is known, F2 is known, D1 and D2 known, L is known. The only unknown will be RB. We can be able to get RB from this equation. Now with RB, the remaining unknown is RA. To get RA, what can I do? I can do this. I have a choice now. In this case, I can still do the sum of moment about B. You remember when you're doing the moment about A, the reaction that you will get is the reaction that is opposed, or the one that is at the perpendicular distance to the pivot on which you calculated your moment. Now, if we do the moment, the algebraic sum of moment about B equal to 0, we have to be expecting to get RA, because RA is at the perpendicular distance to the pivot B. Now, what's going to be the equation? We can see that the equation will be something like this. About B, RA will induce a tendency of a clockwise moment times the length, because that's the distance. While F1 will create, F1 compared to B will create an anti-clockwise moment. And the moment arm will be D2 plus D3 to get the perpendicular distance. Minus F2 as well. F2 is creating that anti-clockwise moment. F2 times the moment arm is F3, and this sum should be equal to 0. And in this equation, as you can see, we have everything except for RA, which is our unknown, and we can calculate our RA. And the value of RA that we'll get will definitely help us to balance the beam. Now, at this point, once I've got RB, I can also choose to use, instead of using the equation of moment, I can use the sum of vertical forces projected on Y. That also can easily give me RA if I've already got RB. I can use this equation. What is it going to be? You can see that that equation previously was minus F1 minus F2 plus RA plus RB was equal to 0. As we have F1, we have F2, we have RB from here, the only unknown will be RA. Means once we've calculated for one reaction, we can use it for the second reaction. We can either use the equation of moment or use one of the equations of the first condition of equilibrium and get the support reactions. And after doing this, we have always to do the check. The check is important because we may have made a mistake in the moment arms in the perpendicular distances. Always check if the sum of loads that you have on your beam are equal to the sum of your reaction to confirm your calculations. This is the first simplest example when we have 2-point load, or it can be as many point load that you can have, acting on a simply supported beam for which the weight of the beam is neglected, is not considered. Now let's take the case where we can be given a beam as an example too. Here we are given a beam. Again, we have a load F1. We have another load F2. You can have as many loads that you have. And here we are told that the beam's mass is 50 tons. And we are requested to get RA, RB, while F1 and F2 is known. We are also requested to get the dead load, the beam's dead load. What is it? Beam's dead load is known as the beam's self-weight. We call it beam's dead load, but it can also be called beam's self-weight. Because you are given the beam's mass, self-mass, it's possible to get the beam's self-weight, which is known as the beam's dead load. F1 and F2 are known as live load. These are reactions, but the weight of the beam is what you call the dead load because it can also have an impact on the reactions. Apart from this, we can also be requested to calculate dead load, okay, the beam's dead load, or it's also known as the beam's self-weight. And the self-weight, as any weight, it's always known as the mass times G. A weight of any object, any body is the mass of that body times the acceleration of gravity. We can also be requested to calculate the UDL dead load. It means this is a load, the UDL that is defined by the dead load of the beam. Now, how do we proceed? Knowing already the distances that are given, this is D1, this is D2, this is D3. Calculating the reactions, we've already done it, but here we may be requested to calculate the reactions without taking into consideration the dead load and calculating the reaction in taking into consideration the dead load. Let's take the first case, first of all. Case number 1. Get RA and RB without considering the beam's self-weight. This comes back to what we've done previously. That's simple. We will do the sum of moment clockwise and anti-clockwise is equal to 0 about A, and the sum of moment about B clockwise and anti-clockwise. This one will provide RB, this one will provide RA. We know how to do it, and the equations for this one about A, it will be F1 times D1 plus F2 times the moment arm, which is made up of F2, D1 and D2, minus RB times the length, and everything is equal to 0. We should be able to get the reaction B, which is the only unknown. Same for the second equation about B. We'll have RA times the length minus F1 times the moment arm, which is D2 plus D3, minus F2 times the moment arm, which is D3, and everything is equal to 0, and we can be able to get RA, similar to the previous example. But now, when it comes to calculate the reactions, let's take second case. If we requested to get the reactions based taking into consideration the beam's self-weight, what is it going to be? The first thing, let's check our free body diagram. We need always to redo our free body diagram in an appropriate way. In a situation like this, we have our load F1 and the load F2. Now, because we are given the mass of the beam, this mass will have an influence on the support. It will definitely subject the support to a certain influence. 50 tons is not that small. Now, in that case, we need to get the resultant force due to this mass. Now, how do we get the weight of the beam if we are given the mass of the beam? We all agree that the weight of the beam will be the mass of the beam times G. Now, this mass is in tons. It should be converted into kg. Everybody knows how to do the conversion of tons to kg. Now, take that mass, 50 10 to power 3 kgs times 9,81. You will get the weight of the beam, which is known as the beam's dead load, which can also be called beam's self-weight. Now, whenever we are given the mass of the beam, we can calculate the dead load by taking the mass of the beam in kg times g. Whatever we get here, it's what we call the weight of the beam, or in an appropriate way, we call it the beam's dead load. Or else you can also use the word the beam's self-weight. And we need to be aware of that. Beam's, the dead load, we're repeating, the dead load or the beam's dead load is the weight of the beam, which will be the mass of the beam times G. Always remember that. It's called the dead load of the beam. It can also be called the beam's self-weight. If you come across either this beam's dead load or beam's self-weight, remember that you have to take the mass of the beam times G to get the weight of the beam. Beam's dead load or beam's self-weight comes back to what we call the weight of the beam. Very, very important. Now, once you have the beam's dead load, you're gonna identify where should it be placed. The beam's dead load or the beam's self-weight will always be at the center of gravity of your beam. It means if this is the total length of the beam, which is D1 plus D2 plus D3, the beam's self-weight or the dead load will always be at half of the length. Because that's the weight, half of the length, because that weight is the center of gravity of your beam. Now, once you place this, it means we'll have a situation like this. We have our beam on the support A and B. We have the load which were given previously, F1 and F2. The beam's dead load will always be at half of the length. That's the weight of the beam or the dead load. You can call it DL. Half of the length, the total length of the beam. And if you have this, if you are requested to calculate the reactions, taking into consideration the dead load of the beam, it will be considered as a force at the same level with F1 and F3. Then you will do your equations of moment about A equal to 0, moment about B, the sum, obviously the algebraic sum, and the moment arm of your weight will be at L over 2. Similar to the previous situation, but here in the equation, we need to consider the dead load if it's requested to be considered. And the moment arm will be at half of the length. Be it when you're doing the moment about A, it means the equation will be, in this case, about A will have F1 times D1, and the moment is clockwise, minus the dead load, or this beam's self-weight, times the moment arm, which is L over 2, not minus, it's plus as well, not minus, sorry, it's plus, because the moment is positive, plus F2 times the moment arm, which should be D1 and D2, D1 plus D2, minus RB times the length, and the algebraic sum should be equal to 0. And we can see the only unknown will be this. That is the moment about A, the sum of moment about A. The sum of moment about B will be almost the same, but we have to include the dead loads. RA, which creates a clockwise moment, times the length, minus F1. The moment arm will be D2 plus D3 plus or minus F2 times the moment arm, which is D3, minus, we forgot about it, the dead load, dead load times L over 2. And this should be equal to 0. And the only unknown is RE. Now remember very well, whenever we talk about the beam's dead load, it's the mass of the beam times G. And that dead load will always be at the center of gravity of your beam, which in one dimension will be half of the length. That's what you call the beam's dead load. In summary, remember very well, the beam's dead load is equal to the mass of the beam times G. And the term beam's dead load can also be replaced by the beam's self-weight or the beam's weight, obviously. Now, when it comes to the other concept, the UDL dead load. What is the UDL dead load? UDL dead load, UDL dead load is always calculated by taking the self-weight or the dead load of the beam over the length. The dead load is in newtons, or you can put it in kilonewtons. The length of the beam, L, is the total length of the beam. Now, what's going to be the unit of the UDL dead load? As you can see, is the dead load over the length. It will be in either kilonewtons per meters or in newtons per meters. This is a unit of a UDL, but it's the UDL due to the dead load. Let's admit that with this beam, which has a mass of 50 tons, the dead load will be 50 tons, first of all, in kg will be 10 to the power 3, 50 10 to the power 3 kgs. The dead load, or the beam's dead load, or the beam's self-weight will be the mass of the beam times g, which is 50 10 to the power 3 times 9,81. You get the dead load in newtons, because kg and newtons and meters per second square will give us newtons. We can convert it into kilonewtons. Then how do we get the UDL dead load? The UDL dead load will be the dead load that we got here, dead load over the length of the beam, the total length. Let's admit that we get maybe 50 10 to the power 4 here in newtons, and the length is 2 meters. What am I going to do? I'll take the dead load 50 10 to the power 4 in newtons over 2 meters. I should be able to get my UDL dead load as 25 10 to the power newtons per meters, and I can express it in kilonewtons per meters. This is how you calculate the UDL dead load. Now, always reminding a quick recap. A UDL, a dead load of a beam is known as the beam's self-weight. We call it dead load, and the self-weight of any object is the mass times g. And the UDL dead load will be equal to the dead load, which is the beam's weight or self-weight over the length. And here it's the total length of the beam, which should be in meters. The dead load should be in newtons, or generally better expressed it into kilonewtons. This is another example. Let's take another example. We're not using numbers. These are examples of concept. Another example. Here we are given a beam. We're taking simply supported beams or statically determinate beam. We have a load here, F1. And here we have an applied moment, clockwise moment. We had another point load here, F3. And this is A, this is B. We may given the same, the distances should be given, D1, D2, D3, and D4. And we are requested to get RA and RB for the beam to be in equilibrium. The moment is known, and this moment can be in kilonewtons meters. The load are also in kilonewtons. This would be an X value. How do we get RA and RB? Again, by use of the equation of moment. Second equation of equilibrium. About A, let's write the equation. What's going to be the equation? We have F1 creating a clockwise, and the moment arm is D1, and the moment is positive. After F1, we have an applied moment on point C. Let's call that point C. The next value given as well. But this moment is already defined as a anti-clockwise. Sorry, a clockwise, as you can see. It means because it's already defined, I will add it as is, plus X in kilonewtons per meters. So in kilonewtons meters, sorry, not kilonewtons per meters, meters. Kilonewtons meters. Plus F2, what is the moment arm? It's D1, D2, D3. And it's a clockwise moment. D1 plus D2 plus D3. Minus RB, which is for the moment arm, which is the length, times L, equal to 0. What is the only unknown we have? It's only RB, because all are given. And let's take the other moment about the second pivot, B, that will allow us to get the opposite reaction. About B, RA will create a clockwise moment, and the moment arm is the total length. But F1, we can see our pivot here. F1 is inducing an anti-clockwise moment. F1 minus the moment arm is D2, D3, D2 plus D3 plus D4. You can see that perpendicular distance. Then at C, we have an applied moment. This moment is already defined. Be it compared to A or to B, this moment is already given as a positive moment. I will just add it as given, plus X, moment in kilonewtons meters, because it's already defined as a positive. Be it, even if I look at B, even if I look at A, we can see the moment is established. And I will keep it like that in the equation. Then the next will be minus F2, and the moment arm is D4. And this algebraic sum of clockwise and anti-clockwise should be equal to 0. As you can see, the only unknown will be that one. Or else I can use the sum of vertical forces equal to 0 once I've calculated RB. And I should be able to get RA. Now here what I'm trying to emphasize on is, whenever you have a moment that is given, use that moment as is in both equations of the moment. It's not going to change. It has to be as is. If this moment was negative with a certain value, whatever it could be, y value in kilonewton per meters, I would have used it in this equation with the sign negative and with the amount y that is given. That's what we need to remember whenever we have an applied moment. It's a case that we can come across. It means if this was in this direction, the sign here would have changed in both equations, because already the moment is defined as a negative moment. And in both equations of moment, I'll keep it as given, because this is an equation of algebraic sum of moment that are acting all the way on the whole beam. And this should be expressed and added in the equation of moment as given in the equation itself. Another case or example. We're not using numbers, but we're explaining the concept, and numbers can be used when you practice it. Now, so far, we've dealt with cases where we only have loads that are vertical, concentrated load or point load that are vertical. But let's assume that we have a case like this, an inclined F1 at 30 degrees, and F2 here, and maybe F3. And we are requested to get RA and RB, while the forces are all known. The forces are in kilonewtons, and they're all known. But we need to get RA and RB. Here we have a point load which is inclined. Every time we're dealing with a point load which is inclined, we always have to use the components, vertical and horizontal components. It means this F1 as a resultant force will be represented by its horizontal component, which is F cos of 30, and the vertical component, which is F sine of 30. Then having these two components will replace the effect of F1 as an inclined component. That's the first thing that we do. Once we've done this, then we can proceed by solving. As you can see, we have now an horizontal component on our beam due to the fact that we had an inclined force. Now, what's going to happen to the support A? If we need to draw our free body diagram, this is how our free body diagram will be. It will be something like this. Our pin support with the two components, RAH, RAV. We have F1 sine of 30. We have F1 cos of 30. We have F2. We have F3, as well as our roller support this side, which has one direction of the component. Now, in this case, this component will have a certain value because the beam on the horizontal will be subjected by this and this RAH. Consequently, the sum of horizontal forces for the beam to be in equilibrium, the sum of horizontal forces should be equal to 0 for the beam to be in equilibrium horizontally. And what do we have horizontally? RAH, which will be triggered by the fact that we have F1 cos going in the other direction. It will have a tendency of pushing the beam that side, while the beam can't move sideways in this direction because of this pin support. Definitely, there will be a reaction. This F1 cos creates an action which will be balanced by the resistance of the beam in this direction. And if we do the algebraic sum of forces on Y, you will see that this equation will be RAH, which is directed toward positive values of X, minus F1 cos 30. And those are the two forces that you have, and this algebraic sum should be equal to 0 to F in horizontal equilibrium. And therefore, from here, we can easily get RAH. F1 will be given, RAH will be then F1 cos 30. And this will give us a certain value of RAH. To get RAV, because it's vertical, we need to use the moment about, the sum of moment about B equal to 0. That equation of moment will definitely help us to get RAV. And once we have RAV and RAH, we can be able to calculate the resultant RA. And to calculate the resultant RA, what are we going to do? We'll use the Pythagoras. It means to get the resultant RA, in this case, it will be RAH squared plus RAV squared to get the total RA. Because in this case, we have a horizontal component triggered by the inclined force that will generate a reaction here. And we should also be able to get the angle. How do we get that angle? We can use the tan. The tan will be the opposed over the adjacent. It means it will be RAH over RAV to get the angle at which the total resultant at A. Because whenever RAH is got a value, we need to remember that we should get the total RA by using a Pythagoras, because Pythagoras will help us to easily get the resultant. And then to get the moment, to get the reaction RB, we know to get RB, we need to do the sum of moment clockwise and anti-clockwise about A equal to 0. This equation will make us generate RB as our answer. Therefore, we'll have calculated our RB on the roller support. We'll have calculated our RA and RAH. If we didn't have an inclined force here, everybody agrees that if there was no inclined force, you will see that RAH, if there's no inclined force, RAH is equal to 0. This RAH will have been equal to 0 if there was no component, no horizontal component on the beam. And that horizontal component is created by the action of the inclined force. Then we need to remember every time we have an inclined force applied on the beam, that inclined force needs to be represented in terms of its components. It has to be decomposed. You need to put the component, the horizontal component and the vertical component. This horizontal component will have an action on the pin support, and that action will generate or will trigger the value of the horizontal component on the pin support. But if we have a beam which, as I'm saying and we're repeating, if there is only horizontal of vertical load, the component, this component on the pin support will always be equal to 0, because there's nothing on the horizontal that can trigger the horizontal component of the pin support. That's what we need to remember also in this case. And another case study, or a case that we can easily come across. We've taken the cases of inclined forces, taken the case of applied moment. We can also have a case of a beam which is loaded by UDL and VDL. You can have a load here, you can have a UVL here, maybe another load here, and then a UDL, and then a support. Now, in terms of concept, as we've said, the very first thing we need to do is to get everything, the resultant of the UVL and UDL together. This one should be splitted because it's a combined VDL. This one will have its resultant. As we know, we need to get the resultant. This one will have two resultant, one resultant for the top and one resultant for the bottom. Just a reminder, whenever we have a VDL on a right triangle, we remember very well that the resultant will always be at the 2/3 or the third. If we're counting from the right angle, this is the length, the third of the length. That way, there should be the point of application. Or if we come in this side, it will be the 2/3 of the length. let's take the right angle as our reference. It means if this is 6 kilonewtons per meters on the length that is 9 meters, the total VDL will be 6 kilonewtons per meters times the length over 2, because we have this, and this will be 27 kilonewtons as a resultant. The point of application of this resultant will be at the third from the right angle. A third of 9 will be 3. It means 3 meters from the right angle. That's where we put our force, our resultant force of 27 kilonewtons. And a reminder for the UDL, that is a simple one. If we have a UDL, if this is 10 kilonewtons per meters on a length of 6 meters, we need to get the resultant, and this resultant will always have its point of application at half of the length. And how do we get the resultant? Take the load per unit of length times the length. This will be 60 kilonewtons, and that 60 kilonewtons will be placed at half of the length. Now, the objective in this kind of situation is to make sure that we get the resultant of the VDL and the UDL. Then we can draw the free body diagram and then proceed by using calculation, by using the equations of equilibrium to get the resultant or to get the reactions that are missing. That's how we proceed when it comes to solving a problem like this. A quick reminder, reminding, very important, when we have a horizontal load, as we said it before, an inclined load, please always use the component. Decompose this inclined load by the component. And whenever we have a situation like this, definitely this component will trigger the horizontal component of a pin support. That's one thing we need to remember. We need also to remember whenever we have an applied moment, an applied moment can be represented like this: a force acting on a vertical member of the beam, or else it can also be represented like this. Now, this applied moment, it's already defined. The direction of this applied moment is already defined. When we do the sum of moment about a pivot, either A, either B, we will only add up this moment, we'll add it with its direction, which is already defined. There is no need to change it. It's not changing even if we change the reference support. If we do the moment about A, this moment being automatically defined as a positive moment, it will remain positive in the equation of the moment. If we do the moment about support B, it will, because it's already showing us that it's a positive moment. For both equations of moment, it will be kept as positive. When we have UDLs and VDLs, we need to get their resultant. Their resultant will be used to calculate the moment. But this resultant, as I'm repeating, this resultant of the UDL and VDL are not point loads, but we consider them as point load when it comes to calculations, but they are not point loads. They are virtual load representing the effect of all these loads that are distributed on a unit of length, on a unit of area, or a unit of volume, depending on how they are expressed. Reminding as well, the dead load of a beam, the dead load is the mass of the beam times G. And the dead load of a beam is just the self-weight of the beam. To get the weight of the beam, if the mass is given, you just take the mass times g. You get the dead load of the beam. Then the UDL dead load of the beam will be to take the dead load over the total length of the beam to get an expression of a UDL. And an expression of a UDL can be kilonewtons per meters or newtons per meters. It's a UDL due to the dead load of the beam. That's why we call it UDL dead load. And there's a difference between a live load and a dead load. A dead load is just due to the mass. A live load is just a load that is applied either on a point, either on a length. That is a live load. Like VDL, UDL, point load are called live load. And dead load is just the mass of the beam that can have an influence on the calculations of the support reactions when it comes to heavy beams, for example. These were different ways of approaching questions when it comes to apply this first and the second condition of equilibrium. Thank you and see you next time.